had gotten to this point where we were actually doing section 4.1. The rest of this was like remediation to help us remember how to do things. And now we're going to talk about angles and their measures, which is what we've been doing all along. So we want to be able to work with DMS measure, which nobody has asked about so far, so obviously that's going well. Some of you did, of course, I'm sure, find the DMS button on your calculator. Obviously, you're not going to be using that. You can use it to check, but we want to make sure that you're able to do the DMS without that. Okay, do you want me to show you where it is, even though you'll just be using it to check? Oh, see, I might have even forgotten where it was because I didn't want you to use it. I think it's math. Found it really quick and easy on my 83 plus at home. Maybe it's not on the TI-84 pluses. It's on the old 83 pluses. I'll have to think about that now. It was easy to find on my other calculator. Right underneath here. It might not be on this one. I'll have to look that up. Like I said, TI-83 plus, I went right under math numbers and DMS with the conversion. Did you find it?
Is it second angle and then number 4? Apps.
Yeah.
Apps.
Oh, the apps. Yep. You got it, Cy. There it is. So on the 84 plus and above, it's going to be second apps for angles, number 4, and that'll change it. But what you have to do is put the angle in first. Like if you have 342.568 degrees, then second angle, number 4, enter. There it is. So, we're going to do them by hand, obviously. We always talk about that, about how it's the algebra that we grade, and then you just back it up with the graphing calculator. So we want to be able to make conversions from degrees to radians and vice versa. Most of the time it's going to be taking degrees and turning it into radians because radians are more accurate. They're based on what we know about a circle. We're going to find arc length with a nice shortened formula and then make connections between angular and linear motion. That's definitely, I think, we're going to have to wait till tomorrow. So those are our objectives. Input variable in a trigonometric function is an angle measure. What angle are you talking about here? And the output is going to be a real number. An immediate problem arises based on our choice of measurement, degrees or radians. Because here's the problem. Degrees have a label. And that's going to affect your answer. Labels carry over when you do your answers. Radians do not have actual units. Notice in some cases they just write pi over 3 and there's no label behind it. And that's because there doesn't need to be. Radians do not have a label. Now why does that happen? Here's why. That is a circle. If we want to find the circumference of a circle, do you remember the formula? How do you find circumference of a circle?
2 pi r.
2 pi r. Do you see how the 2 and the pi are even built immediately into the formula? It's already a part of this. So when you find your answer, you don't say whatever the label is for radians and then inches, feet, miles. You just say inches, feet, miles based on what you have for the radius. So that radian measure is built into a circle. It's kind of a perfection piece that we like to have. So it doesn't have a label. So we definitely prefer that. Degrees have no mathematical relationship whatsoever to linear units. There is no way to say, hey, if we took all these 360 degrees and we stretched them out straight, this really cool thing would happen. Nothing cool happens. It's just 360 degrees lined up straight. Nothing cool happens. But if we cut this circle and unwrap it, it will still be 2 pi r. The length is built into it. So there are 360 degrees in a circle of radius 1. However, there is no explanation for how the 360 relates to that one. How is that linear relationship with the radius explained? And it's not. It's just not. So degrees are an entirely different unit of measure. It was fantastic that it was developed so long ago when they were able to get that sexagesimal system down and work with it the way they did. It really gave us a lot of good math, but it's not the best way to go. So down here, this says these are the pictures that motivated trigonometry. So we've got this diagram here of a right triangle with an H and an S. I don't know about you, but the first thing I think of with trigonometry is opposite over hypotenuse, sine. We could get that angle. But back in those days, they didn't have a lot of trig tables and they didn't have that information. So their question was, how could you make a system that would make this work? And here's what they did. They took a circle with a radius and they drew a triangle based on a chord of that circle. So this is a chord. Remember, a chord is a segment that has its endpoints on a circle. And they said, well, if we do this, there has to be something special about that relationship. And there absolutely is. So as we read this down here and we look at the pictures and see what are they trying to figure out, it says in the above diagram, the ratio of S to H in the right triangle is always independent of the size of the triangle. It doesn't matter if I make this a huge circle or a little circle. The ratio of those two sides is always the same. That's where we get the trig functions from. So remember your similar triangles from geometry. As long as they have the same shape, but they're different sizes, they're considered similar. In this diagram, S is half of a chord. Well, here's my little chord picture, and S is half of that piece right there. And it says that that is half a chord in a circle of radius h. So they're matching up all of these pieces to a circle. And in this diagram, S is half a chord in a circle of radius h, and theta is called the central angle. Yeah, that's been a while too for you guys. Central angle just means it's formed at the center of the circle. So theta would be the central angle that's formed at the center of that circle. Intercepting a circular arc of length A. Here's that A. So this piece right here is going to be that A. The arc determines, come on, the angle leading to a radian measure. So they're saying if we can figure out what's going on with that arc, we could work backwards and we could talk about that angle in terms of radians, which is exactly what we want to do. It does not have a label. We want those radians so everything is in terms of pi, as circles should be. So a degree represented by our little bubble symbol, which we've already seen, and if we don't see the bubble, then we know it's in radians, is a unit of angular measure equal to 1/180th of a straight angle. In the DMS system, the degrees, minutes, and seconds system of angular measure, each degree is subdivided into 60 minutes. Like I said when we went over this, it's very easily to think about this as hours, minutes, and seconds, because that's exactly how the system works. And then each minute is subdivided into 60 seconds. And they use the apostrophe and the double apostrophe to show the labels on those. So the labels are going to be really important to us as we're trying to figure out, okay, how does all of this system work here? Example 1, working with DMS measure, convert 37.425 degrees to DMS. Well, the first thing I think is, well, I already know it's 37 degrees. Got that. Now I need my minutes and my seconds. Well, that comes from the portion that remains back here. So I'm going to need 0.425 times 60 to give me my minutes. I suppose I better keep this handy. So 0.425 times 60. I'm only writing down the 25 because that's the portion I would use for the minutes. But I still have a half of a minute left. So I'm going to take that 0.5 that's left and take that times 60 to figure out how many seconds are remaining. So in DMS conversion, this would be 37 degrees, 25 minutes, 30 seconds. And that's, it's not that tough to do. That's the reason we say, just show the work. You know it's on the calculator, but you're probably not going to remember it's there because hopefully you won't be using it a whole lot. It's kind of hard to find. So convert backwards. 42 degrees, 24 minutes, 36 seconds. Okay, so this was the 42, but I'm going to have to add 24 out of 60 because there's 60 minutes in a degree, plus, how many seconds are in a degree? 60 times 60, 3,600. Because we know this is going to come out as a nasty decimal, we just grabbed a calculator to punch all this in. Let it tell us what the good news is. So 42 plus parentheses 24 divided by 60, parentheses plus parentheses 36 divided by 3,600. And there we have it, 42.41 degrees. So there's the forwards and backwards process. The part that I found that students have the worst time with is right here. Remembering that this needs to be 3,600. Because if we want to convert it to degrees, we have to think how many seconds are in a degree and go all the way back. But that's the toughest thing of that whole system. That's it. So down here, in navigation, which is one of the main reasons that they did so much with trying to travel by the stars at night and that kind of thing when they were sailing. In navigation, the course or bearing of an object is sometimes given as the angle of the line of travel measured clockwise from due north. Now that messes with what we know because when we're measuring angles, our standard position is always that positive x-axis. But they were there first, so they said, here's due north. So if we want to tell somebody how we're traveling, we're going to say it's 155 degrees from due north. All right, well, we just have to be careful when we're reading the word problems. What are they telling us here? So this has the course of a fishing boat bearing 155 degrees out of Gloucester. Now, how are we going to know that we're supposed to go from due north? Right here, everybody, this little word. Bearing. If we see bearing, due north is where our angle is going to start from in those word problems. So, little teeny word underneath your little drawing there that's going to tell us who they're talking about that due north. A lot of times they'll explain that anyway. They'll say a bearing 155 degrees from due north, because they know we want to think of standard position as a positive x-axis. In this book, degrees to measure angles in their geometric context, especially when applying trigonometry to real-world problems that involve surveying, construction, and navigation, where degrees are still the accepted units of measure. Every once in a while when they're doing new construction, you'll see a surveyor out there, they've got all of the gear on that has the neon stuff on it so that you see them. And their little surveying machine, and they're looking in that little thing to see where is this going to go. A lot of that is still based on degrees. So we don't want to throw degrees out. We just want to say there's something a little better if we're talking about perfect answers. And in math, those perfect answers are called elegant. And that's what we always want in math, is elegant math. So when we work with our trigonometric functions, we're going elegant. We will measure angles in radians so that the domain and range values can be measured on comparable scales. It doesn't have a label. Radians just are. It's the way circles work. So if we get to choose, we're going to choose radians. What is a radian? Well, a radian. A central angle of a circle has a measure of one angle if it intercepts an arc with the same length as its radius. Oh, interesting. If you have something with color on it, have something with color. Because here's what we're saying. We're saying we're starting on this positive x-axis. this is obviously our radius right here. Oh my goodness, that's not readable. I have to draw an arrow or something. And yeah, there's colored stuff in the bag too. Here's what they're saying. If we want 1 radian as our angle, whatever this is, we want to draw an arc exactly the same length. So this length and this length are exactly the same. And I know it looks odd to put those hash marks in there like you did in geometry, but I'm saying those lengths need to be the same. When that happens, this angle right inside here, that central angle, is going to be 1 radian. All works because of circles and the cool stuff that goes on inside of circles. So, down here, I thought about giving you the pieces of string, and then I thought, no, I want us to think a little deeper than string. You know, I want us to think about this as we're drawing it and use our mental skills. So, it says, carefully draw a large circle on a piece of paper, either by tracing around a circular object or by using a compass. Identify the center of the circle as O. Now we've got one down here, so everybody has the same one, but we want to label that O for the center. And where else are we supposed to label? And draw a radius horizontally from O toward the right, intersecting at point A. So that would be our point A. And then it does say, cut a piece of string or thread. And what we're going to do is we're going to place one end of our radius right here and kind of mentally show where we believe that 1 radian would be. So let's take a crack at that. This long. There, that doesn't look too bad. So if these 2 lengths, those 2 distances are the same, then I have just produced theta here, a central angle of 1 radian. Now here's the reason that I didn't want you to do the string. I want us to think through this. Think in radians. How many of these radians are we going to be able to fit to get over here? Pi. So 3.142 of them. So we'd have 3 and just a little bit more. And that's the answer to one of the little questions up here. How many radians must there be in a completed circle? Well, that's 1 pi. So our 3.142, if we multiply that by 2 to go all the way around, well, let me just put it up here so that we're not getting confused by the math part of this. Glasses, Cedar. There we go. So 6.283 for all the way around. 3.142 to give you the straight angle, but 6.283 get us all the way around. And that brings us back to the circumference of a circle in terms of its radius. And circumference in terms of the radius is 2 pi r. Why did they say in terms of the radius? Because we want to talk about radians, we're going to use the radius. Circumference can also be found by pi times the diameter, but that's the geometry way to do it. If we want to talk about trigonometry, we want to think in terms of the radius. Now it says if we cut a piece of thread 3 times as big as the radius, so we take this, 1, 2, 3, are we going to get all the way to the other side? Nope, we're short. Because pi, 3.142 rounded to 3 decimal places. How many radians are in a straight angle? Pi. So we have to think in terms of pi. And the visual helps a lot, because once you draw the circle, you go, oh, wait a minute, this is 1 pi, this is 2 pi. And you start to put all of that together. So this was really good as a visual. I'm not sure the string would have helped us much, so that's the reason I didn't give you any more pieces of string. 1 degree in radians. So I'm going to start with 1 degree, and I'm going to figure out how to get that to be a radian. Well, to do this, in math we call this unit analysis. In science they call it dimensional analysis. We focus on the labels and trying to get rid of what we don't want and put in a new label that we do want. So right now I've got 1 degree over 1. And here's what I know. If I'm going to get rid of those degrees and put something about radians, I have to have something about degrees on the bottom, because then the labels will cancel out. That's the unit analysis. The units up here are degrees, the units down here are degrees. But I want my answer to be in radians, which means I need something about radians up here. And normally we wouldn't put a label RAD up there because radians don't have one. But just so everybody can see, we're using unit analysis. We're checking those labels. So I think, what do I know about radians and degrees? That's what we know. These are going to cancel right out. And our answer will be top times top, bottom times bottom. And that's why we use pi over 180 as the conversion. Now, if we really wanted to be nitpicky and say, well, let's see what this is, 2 to 3 decimal places. Second pi divided by 180. 0.017, yeah, I'm going to go 1 more decimal place here since we had so little to work with that 0 in there. 0.0175 radians. Now, why do that? Because part of the homework is probably going to give you this and ask you to work your way back to this. So the next one says, how about if you have 1 radian? Well, first of all, slap a 1 under it. And you want your answer to be in degrees. Well, then my radian label better cancel out, and I better have something with the bubble about degrees up there. That's the only way that's going to happen. But we still know the same thing. We know there are pi radians in 180 degrees. Radians are going to cancel out. 180 degrees over pi. And again, we can punch that in if we said, hey, we've got to round this. So 57 point, we go 3 decimal places, 57.296. Degrees for each one of those. So now we're going to do some conversion. And I'm going to tell you that for A and B, we shouldn't need to use the formula. We should start thinking in terms of radians. And always getting this picture in our head of, hey, this is pi, this is 2 pi, and think in those terms. So if we have 90 degrees is right here. What part of pi is that? 1/2 of it. So 1/2 pi, pi over 2. Could you do 90 times pi divided by 180? Absolutely. Is that going to help you with what you need in the future? Not a bit. This will. Because you'll start to envision, okay, 90, wait a minute, that's pi over 2. I can't do 90 degrees. I need pi over 2. What pi over 3? So here's our pi. Going to divide it into 3 equal pieces. How much would each of those pieces need to be in degrees? They'd have to be 60. 180 divided by 3, 60 degrees. Could you multiply by 180 over pi? Absolutely, but bad idea. And we want to get, especially for the nice ones, we want to be able to identify those very quickly. Find the length of an arc intercepted by a central angle of 1/2 a radian in a circle of radius 5 inches. Oh my, okay. So the measure of the whole arc is the circumference. But they're saying we don't want the whole circle. Okay, well, what portion do we want? We want half a radian of the circle. So 1/2 of a radian over the 2 pi radians is what we would want. Oh, well, the 2 pi's are going to cancel right out. And we're going to get 1/2 times the radius. So 1/2 times 5, which is 2.5. Now this was in inches. And what I just did was try to show you it's silly to do them this way every single time. Because the 2 pi's are going to cancel out no matter what. And we're going to get r times the angle. So sectors we use an S for. So the sector length is what we're looking for here. Is going to be r times theta. But only if theta is in radians. It has to be in radians. So here's the big catch. Theta must be in radians. Because this formula that we just derived didn't come from a formula with degrees in it. It came from a formula with pi. So if we can get degrees into radians, then we can just use this very simple, sweet formula. S equals r theta for arc length. Find the radian measure of a central angle that intercepts an arc length of S in a circle of radius r. Well, I got a formula right here. They want me to figure out what the angle is going to be. How do I solve that for theta? Divide by r. So using this very simple formula, we can find anything that they need, as long as they give us 2 out of the 3 variables. As we go through them, we can work backwards and find whatever we need. So we do have the degree radians conversion. When they're nasty, yes, use the degree in radians. But for 90 degrees, for 30 degrees, for 60 degrees, for 45 degrees, try to think through it visually. That's going to help you as we go through it. With practice, we can perform these conversions in our noggin, in our head. The key is to think of a straight angle equaling pi. We're so used to 180 degrees. We want pi when we do that. Since a central angle of 1 radian always intercepts an arc of 1 radius in length, it follows that a central angle of theta radians in a circle of radius r intercepts an arc of length theta r. That's where the formula comes from. And here is the little formula right here. But again, I need you guys to underline this, maybe in a different color, circle it. It only works in radians. Don't try and use this formula in degrees. It works in radians only. So if you're looking for arc length, first thing you do, is it in degrees? I better convert it. Because if I convert it, then I can use this sweet little formula to figure out that arc length that I need. So, does a radian have measure? Does it have units? It has measure, it doesn't have a unit label. So the formula S equals r theta implies an interesting fact about radians. As long as S and R are measured in the same units, radians are unit neutral. They do not have a label. For example, if R is 5 inches and theta is 2 radians, your arc length, it wouldn't make sense to say it's inches radians. It's not, it's a length. So it's just inches. We don't use that label because radians don't have one. This unusual situation arises from the fact that the definition of the radian is tied to the length. You use the length of the radius and the length of the radius in order to figure out that arc length. So, unit neutral. But again, arc length formula, degree mode, I don't want to measure. I don't want to figure out another formula and have to memorize another formula. This is in my head. I just always do S equals r theta, and then remember theta has to be in radians. So I do the conversion to radians first, and then I put it in the formula. They're saying if you want to memorize a totally different formula, you could actually put the conversion right in the formula itself, which is silly. You know, if we know the two formulas, we should just convert, throw it in there and see what we get. So example 3, it's beginning lunchtime. Pizza sounds good. Perimeter of a pizza slice. Okay, perimeter. Peri means around. So we want to know all the way around this pizza, how far we're going. Okay, well, I already know 14 of it. Find the perimeter of a 60-degree slice of large pizza. Okay, so I need this. Hey, that's arc length. I know that formula. Oh, but wait, theta has to be in radians. Okay, so theta. Said this is 60 degrees. How many 60-degree wedges will fit in our 180? 3 of them. So it's pi over 3. So that arc length is going to be 7 times pi over 3, or 7 pi over 3. But they probably want it as a decimal. They don't want us telling them 14 plus 7 pi over 3. So we have 7 plus 7 plus 7 pi over 3. And 14 plus 7 times pi divided by 3. So 21.330. And it was perimeter, which means we're looking at length, and these were all in inches. So again, it's not inches radians. Radians doesn't have a unit label. Example 4. Whoops, question. Okay. Designing a running track. Those of you that are in track, you know there's a reason they stagger you at the beginning, you know, so everybody's going the same distance. The running lanes at the Emory Sears track at Bluffton College are 1 meter wide. All right, 1 meter from here to here, then it makes sense that if this one's 33, that one's 34. Okay, so far so good. The inside radius of lane 1, 33. Go one more, 34. How much longer is lane 2 than lane 1 around the turn? All right, well, that is arc length. But what's theta for both of those? From here to here. Pi. It's just pi. So the one on the outside has a radius of 34, so that'll be 34 pi. And if we want to know how much more it is, we're going to subtract the inside one. So what's the arc length of the inside one? 33 pi. Oh, I'm liking this one. 34 pi minus 33 pi. 1 pi. 3.142 meters. And that's why they stagger you at the beginning for longer races, because what they want to do is make sure that in the end everybody's running the same amount, you know. And obviously by being further out, you're running more as you go to those corners. So, we got a regular bill schedule. Excellent. Now, in applications, it's sometimes necessary to connect angular speed, measured in units like revolutions per minute, to linear speed, measured in units like miles per hour. How many times does the tire turn when you travel a mile? You know, those type of things. You want to know that. This means we need to connect the two by one of the arc length formulas or by using conversion factors that equate 1 radian of angle measured to 1 radius of arc length. They make this sound much more complicated than it is. Again, it's unit analysis. We're going to try and convert what we already have into what we want. So we're working with what labels do we need to get rid of them and pick up a new label that we want. So down here in example 5, it says, Albert Juarez's truck has wheels that are 36 inches in diameter. Oh, well, that's great, but I'd prefer to have a radius, so not going to make any difference in the end, but I know that that's half the diameter. The wheels are rotating at 630 revolutions per minute. Find the truck speed in miles per hour. Oh goodness. All right, so obviously this is a piece of info I need here. 630 revs per 1 minute. But there was another mathematical piece of information up there. 36 inches in diameter. Well, that would make sense because we'd want to know how far does it take to go around the tire once, all the way around it. All right, so to know that, I would do S equals R theta. But we're going all the way around. So theta is too high. So it would actually be 36 pi. Now why did that happen? Because arc length all the way around a circle is called circumference. And circumference is 2 pi r. That's how all of these are linked. So if you don't want to use arc length, you can just use 2 pi r, or even in this case, faster one is pi d, pi times the diameter for circumference, because we're going all the way around. Now, I'm going to write rads up here, just so everybody knows that's radians. But it's going 36 pi radians in 1 time around. Well, isn't 1 time around called a revolution? Isn't that 1 revolution? Now let's see what we have and let's see where we need to go. These revs are going to cancel out. Now, this 36 pi was in radians, but it was also about going all the way around. So I go back and I see, well, that was actually in inches. So I'm going to take that radian piece off of there because I know it's radians, and it's just that length of inches that I have. So right now, my label, top times top, inches. Bottom times bottom, inches per minute. I don't think they asked us for inches per minute. Miles per hour. Okay, we've got some work to do. So let's start with the minutes. Let's convert with minutes until we can get to hours. So let's see. There's a minute on the bottom. I'm going to need something about minutes on the top, and hopefully I can connect that up to hours right away. Do you know something about minutes and hours? Cool. Now we check our labels. Inches per hour. Miles per hour. Okay, so we're going to need something about inches on the bottom, and on the top we want to make it bigger, so the next bigger unit of measurement would be feet. You know anything about feet and inches? What do you know? 1 foot, 12 inches. Inches are gone. Now we have feet per hour. Oh man, now we got to remember the hard one. Let's see, feet is on the top up there, so feet have to be in the bottom because I had right too big, so it's all fitting on there. Something about feet, and I think we have something about miles that we know is linked to feet. Do you remember it? 5,280 feet in a mile. The feet will cancel out. That's why this is called unit analysis. My focus this whole time was not necessarily on the numbers, it was on making sure that those labels would cancel out. So now if we do top times top times top times top times top, divided by bottom times bottom times bottom times bottom times bottom, it'll be in miles per hour. So let's see what we get. $630 times 36 pi times 60. Everything else up there is ones. Divided by parentheses, we've got a 12 times 5,280. 67.473 miles per hour. All from the unit analysis, making sure that if we needed something gone, we had a matching label top and bottom, so that we could cancel those labels out. All right, a lot of stuff today. We've done lots of pieces of the objectives. So our objectives, we were talking about working with BMS measure. Don't think that's an issue. Making conversions, degrees to radians, and then finding arc length. So 43210, me on how you think things are kind of wrapped up today with all this good stuff. Okay, so lots of threes. So you're not necessarily feeling totally confident, but you're feeling pretty good. And that's a good place to stop. So you definitely can finish those few problems in that worksheet. And now this is going to look scary.
Oh, that is.
It's not. Because, again, you're going to find we didn't talk about nautical miles yet. So you're not going to be able to do this whole thing, you know. Not that there's a lot of nautical miles in there. But you'll be able to finish up those few problems that you had left from the worksheet. And then do almost everything on this. And basically, this is just review of stuff we've already done in the worksheet. But we need to see some more examples of that as we go through. So when you get to the thing where it's talking about stat miles and not miles, tell yourself, oh, I better wait. We didn't talk about that yet. That'll be the one topic we need to cover tomorrow, and then tomorrow you'll have a big chunk of work time as we have another wonderful worksheet about this stuff. One of the things we